Welcome back. In this video, I want to show you a code demo for logistic regression, especially for OR and AND gates. Just recall, since we have had some distance from this, what we mean by this. So remember, logistic regression was a simple classification algorithm. And when we are given some data, let's say some data of the sort of an OR gate, which has 4 possibilities, 0, 0, 0, 1, 1, 0, and 1, 1. Then we typically get 0 only at one place, which is at 0, 0. And everywhere else, we basically get, this is 1, 1. Everywhere else, we actually get, and this one should be 1, 0. Everywhere else, we actually get 1. So this is what is made as the table, that when x1 is 0, 0, then the ground truth is 0, and everywhere else, it is actually 1. As I had told you during our logistic regression discussions, basically the classification line goes somewhere here, so that every data here would be labeled. If I give some arbitrary data here, it would be labeled as 1, and any arbitrary data on this side, that will be labeled as 0. This is supposed to be a proxy for a lot of data points here and lot of data points here. And of course, we are just giving 4 data points just as representative data points. So our data size is a limited data set size. This is equal to 4. And the model with which we are trying to accomplish this is the graphical model, or that I have shown here. Here you have y and of course, or y hat, and you put a filter here. If greater than 0.5, then you call this 1. If it is less than 0.5, we call it 0. I hope you recall all this. And the model here was, of course, W0, W1, W2. Then it's a summation. Z is W0 plus W1 X1 plus W2 X2. And that's the output here. And A hat is Y hat. That's the output here is what we call A hat. And that's, of course, sigmoid of Z. Recollect that sigmoid is 1 by 1 plus e power minus Z. Finally, we had our cost function. This was the binary cross-entropy cost function, and that was given as minus y ln y hat minus 1 minus y ln 1 minus y hat. Recollect that we had the calculation that del j, del z, if you calculate it, always comes as y hat minus y. And we use this finally in backprop and calculate del j del w0 and del j del w1. And del j del w0 was y hat minus y times x naught. Del j del w1 was y hat minus y times x1. And del j del w2 was y hat minus y times x2. So all this is just to remind you of what we had done here. The idea, of course, is in this case to start with arbitrary W0, W1, and W2, just some random weights. I had given you in the video in the 9th week some heuristic arguments on how to come up with W0, W1, W2. But here we wish to do a full gradient descent solution. And what I want to show you in the video that comes, the code demo that comes, is that I can use the same gradient descent idea to find OR gate and to find AND gate. But it turns out it doesn't work for XOR gate. Why it doesn't work for XOR gate will be a little bit interesting. But as you remember, that's basically because XOR gate is not linearly classifiable. But nonetheless, let us look at the examples that I'm going to show you shortly on code. So let's move on to the code. This was just a short video to remind you of the theoretical answers that we had so far, and we will move on to the code using this. So I'll see you in the code. Here is a code that you should find within your directories. It should have been shared by NPTEL. So I have now written a general logistic regression code for a two-feature example. So this is the data that I showed you earlier. Then we basically are treating it as if there were just 4 data points, 0, 0, 0, 1, 1, 0, 1, 1. And on the right-hand side, in the output column, of course, you have y, which is the ground truth. That is for 0, 0, it's 0, etc. Okay. Now, our forward model is decided by the simple model. Z is W0 plus W1 X1 plus W2 X2, and Y hat is sigmoid of Z. So that's what we are trying to impose here. Now, here's the data set. I have just written it in this way. This is just MATLAB style for writing these 4 data. We can write it this way too. It just makes it a little bit more compact if I write it in the way that I wrote earlier. But as you can see, 0, 0, 0, 1, 1, 0, and 1, 1. And I have the appropriate Y outputs here, 0, 1, 1, 1. Okay, so I'll just go back to the old style of writing it. I have just written it as 0 for this, 1 for this, 1 for this, and 1 for this. That's the ground truth. So this, of course, is the general input. Now, what we are going to do, as written here, is we are going to fit a logistic model to this data. All really we are doing is we are squeezing the linear output, which is Z, W0 plus W1 X1 plus W2 X2, to lie between 0 and 1, which is our requirement. Okay, basically using a sigmoid activation function. So I'll just write it in 2 lines here. The linear output here is Z, or what we call linear activation, basically. So this is the way I have written it. I have written a general code. This basically M here means the number of data points. In this case, we have only 4 data points. Later on, when I show you the XOR gate, I will just hard code this. That is, I will just assume M is equal to 4 when I use a full neural network. Now, in this case, I have actually used an extra columns of 1, set of columns of 1. You might recall this from our linear regression case. We used to use this all the time, just so that we can have a simple bias column here. So I'll just demonstrate what X looks like. So you can see on your screens, X looks like 1 in the very first column, and then you have 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so the purpose is really simple. Purpose is to use the bias units appropriately. Now this, I am going to use stochastic gradient descent, but we are going to use 20,000 epochs. Why 20,000 epochs? I have just chosen a random number. The number of epochs could be lower, could be higher. It really doesn't matter too much because this is a simple enough case. And I have chosen some a random gradient learning rate value. As we saw earlier, if you use too high a learning rate value, you get into trouble. So I have chosen alpha equal to 0.1. Okay. Now here comes the interesting thing. What I have done now is basically updated the W. Okay, or I have actually started with some random guesses and actually have done a full-scale logistic regression gradient descent. So what I will do now is actually I will step into this code, to the logistic regression gradient descent code. Just give me a second. It does not seem to be loading properly. So let's see if we can make it load properly here. So I managed to load this code. So here you notice this is basically a gradient descent code for logistic regression. I have assumed the binary cross-entropy loss function. Now the code is written a little bit generally. So it should actually work for if you try to use it for any number of features. Here I am going to show you just for 2 features, X1 and X2, but you use some other problem with large number of features. Regardless of what that problem is, this code should work because it has been written that. The assumption is very simple, that you have some input X, you have some output Y with some labels. and W are the weights. Okay, so the weights are what we are trying to discover. Now I have set some default values here. In case I had not given the number of epochs, it will set it to 4. Alpha would be set to default at 2.8. You need not look at all these. This one reads the data and just finds out the number of points and number of features. So for example, we now know once you read here, let me step through this. You will see that it automatically knows that there are 4 data points and that there are 3 features. Why 3 features? There is the bias and then there are the 2 extra features. So when I do this, you can see that it just initializes these 3 weights. The first weight 0.7513 is the bias. It's initialized randomly. Then you have 0.2551, that is W1. So the first W0 is initialized to 0.7513, W1 to 0.2551, and W2 to 0.5060. We had already declared 20,000 epochs, so n epochs is 20,000. And I'm just going to cycle through that, and we are doing a batch update. Sorry, I said I'd do a stochastic gradient update, but looks like I'm actually going to show you the batch update code. So here, once again, we have the opportunity to go to the batch update code. So this is part of this main code only. I have written the batch update code. Once again, all this batch update does is takes the data. Data is visible on your screen. All the biases, the bias terms 1111, then the original data 00011011. The ground truth for that 0111. The current guess for W, and you can also see the current learning rate alpha. Now, what does this do? So notice this portion. This is pretty universal. You will be surprised that more or less, except for maybe this term, this is how even complicated neural networks could look. Okay, so all you would do is have a forward pass. So this here, YH, is basically the forward pass. So the forward pass is this. What you do is you go to the model, and you can see the model here, the logistic regression model. You have the linear step, and then you have the non-linear step. So just a combination of these two achieves the forward model. So if we see what happens here, we can quickly check what happens when we look at the forward model. You see the whole X has come here. You have our current guesses for W. So you basically do X multiplied by W. So what that will give you is Z. Okay, so you can see 4 different Zs. What does this correspond to? Each one of them corresponds to one forward pass through one example. So the first Z corresponds to the 0, 0 data point. The second Z corresponds to the 0, 1 data point, then 1, 0, and finally 1, 1. So we are doing 4 different forward passes. If you write it in this way, you can do it at one shot. This is just a vector implementation or a one-shot implementation of this entire batch. Now, once we do that, all we are finding out is y hat, which is sigmoid activation function. So I will do that too. So when I do that, for each Z, I get a y hat. So what really we are doing is, instead of putting a for loop outside and saying for data set going from 1 to 4, do 4 forward passes, I have just done it as a vector. When I show you the neural network using backprop for XOR, I will actually show you a step-by-step implementation of this. But this is just a simple, elegant way to do it. And really, this is how practical neural network codes are written. But it's easier to see when we see the simple case of a logistic regression code. So here, back to the original code, we now have y hat calculated for all 4 passes. So notice what has been done. We had X, which was the original data. We had Y, which is also original data. We have a guess for W. Now this guess for W mixes with the guess for X, and you actually get what the forward passes. You actually get a value for Y hat for each value of X. Okay, so please remember our original picture. Given a value of x, given a value of w, you get a value of y hat. So you can see that right on your screen here. Now, delta, of course, is the error. Okay, so the error in the output, you can see, you have a whole bunch of errors. Now, the advantage is we knew the gradient calculation was, if you remember, x not multiplying y hat minus y. I had shown you this in the initial theoretical calculation, and I had also shown you this in week 9. Then x1 times y hat minus y is del j del y at w1. So you can see the original guess for del j, dj here simply represents the three gradients del j del w naught, del j del w1, and del j del w2. So you have these three calculated here, and of course we are summing over all four examples. The reason I have written it like this is just to ensure all the matrix multiplications work out. So you have four different errors for these four different forward passes, and then you multiply with the appropriate hexes. So once you do that, so let me do that here and come till here. You now have DJ. This is the updated three different gradients that you have. Okay. So 0.2661, minus 0.2419, and minus 0.2325. Once you do that, multiply by the appropriate alpha, you get the new W. So the old W was something, you remember 0.6771 or something of that sort. Now you have an entirely new W. And once we go back, one epoch has passed. Okay. So I step here. I can now find out what the new y hat is at this new value of W. And I can now find out what the cost is. Okay. So if I look at it, my new cost is 0.3833. So this is the cost for guessing W to be whatever our current value, older value was. Now, of course, we have to now repeat this 20,000 times. Okay, so if we keep on repeating this 20,000 times, we will basically get a full update of this logistic regression cost function. So we can come back here and try to go back to here. So when I do this, I'll come back here now. When I come here, actually the number of 20,000 epochs have passed. You can look, J list will be a long vector, 20,000. So you can see slowly your costs are actually reducing. Okay, so let me see if I have plot of the J list. And I don't seem to have that here, but I can plot that before anything else. A little bit here. Let's see if I can plot that here. Well, I'll skip that. Let me actually come back here and show you something a little bit more interesting. So come here and we try to plot what this entire function looks like. Okay, so I'll come here. So you can see the 3D plot of our y hat. So notice these 4 points. The point at 0, 0, the point at 0, 1, the point at 1, 0, and the point at 1, 1. This is what we want to match. Okay. The function that it is predicting is somewhere like this. So it's actually predicting a function. Please notice that our neural network, or in this case, the logistic model, is basically simply a function. You can look at it from various angles. If you look at it from here, it more or less looks simply like the sigmoid. Okay, so, but from a different angle, from a top, when you look at this, you will notice that there is actually a sharp line here, which classifies it as either belonging to one side, either belonging to 0 or belonging to 1. In fact, if you wish, we can now plot what that line is. So let me just go here and continue. I'll come to here. We can continue here and take a step. And let's see if that is plotted. So yes. So this, of course, the top here was the 3D plot. And this is the 2D plot. This red line that you see on your screens is the classifying line, the line for z equal to 0. The z equal to 0 line is basically plotted. You can see y equal to minus w0 plus w1 x1 by w2. So you can basically just create this line very easily. So that's what I did. You can go through the code and figure out how I drew this line. But basically, it is a line, the values of which are given here. We can actually check the values of w. So w, you can see, is approximately w0 is minus 5, w2 is 10, and w3 is 10. So you can think of this, if you take a ratio, as minus 1, 2, and 2, which is pretty close to the values that we had given in the previous video. So you can see this nice logistic regression. We started with some random guess for w. When you go back to this code and check, we had actually given a random guess for w. And from that random guess for w, we got these converged values and these nice plots for OR gate. So the way this OR gate was achieved, I hope you can notice, I had again shown you the sort of top view of this. I don't know if I can achieve that once more. Yeah, here it is. So this top view from here, x1 and x2 shown here, you can see this nice straight line, which changes from, you can see, from dark blue to dark yellow. As further and further you move away from this line, it gets more and more sure that it is 1. The further and further you move towards 0, it gets more and more sure that it is 0. So this is an example of simply using logistic regression for the OR gate. We can repeat this exercise for AND gate as well. And really nothing changes other than the data. So we can see that here, AND gate, same, except now instead of being 0, 1, 1, 1, which was the case for OR gate, it is now 0, 0, 0, 1. So you'll see that literally almost nothing else has changed. The only thing that has changed is the data. So if you compare this code here and this code here, you will see I have changed nothing other than y. And the rest of it is probably verbatim exactly the same. I did nothing other than use the same logistic regression gradient descent. I'm not going to change the code also. So this is the power of the approach. The power of the approach is any data you give, you basically are just playing with the data set in order to create a model. Of course, the weight is going to change. The model is entirely different. So if we run this, let's try running this and seeing. I hope I have not made any errors in the interim. So now you can see. So it has figured out an entirely different model, a different set of weights. So 0, 0, 0 for these three values, and it is now shot up to 1. Again, we can probably try rotating this. Yes. So if we try rotating this, you'll see you have a model which is sort of diametrically the opposite of what we had earlier. It is surer about 0 here and surer about 1 here as you go further and further away. And I don't know if I have drawn the z equal to 1 line, so I could probably do this. And we can run this code again. I can see whether, yeah, so you can see this. So the classifying line has now, is the red line, it has now moved. That's because W0, W1, W2, or W1, W2, W3 have changed. So the values of W, let's keep those values here. Let me just check and run this once more. So you can see it is now minus 13, 8.8 and 8.8. So it has chosen something like minus 3 by 2 and 1 by 2, 1 by 2, or something of that sort. So roughly, again, similar to the cases that I had shown. No, this is not 1 and third. This is 1, 1.5, or something like that. Okay, so 1, 3 by 2, 3 by 2. So it is approximately somewhere. But the remarkable thing, once again, is that it does find a classifying line and it finds it simply by iterating using some blind process such as gradient descent. Now, we might get excited. Let me now clear all this output. And suppose I change this to, let us say, let's go back to the OR gate example, just in case, because this is pros, and I make this something like XOR. Okay, so I put the XOR gate, which is, or I think actually I should switch this to 1001. It doesn't matter, 0110. Yeah, 0110 would be XOR. So suppose I run this. So the question really is, does this converge or does this not converge? So when we run this, let me just go back, run this case, you will actually find, I'll continue and run the whole case. Let's run this too. That it actually does not classify well. You can see the model. The model is a really bad model. Okay, it has made some arbitrary classification line, which is not the correct line at all. Okay, in fact, if we look at the list that we have of J, I can now write this. You can see it seems to have converged, okay, but it converges right from the beginning. Okay, so it's not really moving from the beginning because it finds out some arbitrary W's which satisfy whatever guess it has. Okay, so it is, W is basically, you see 10 power minus 15, W is 0, 0, 0. So the best it can do after a first few initial guesses, it does converge, but it converges to bad values because this is simply a bad model. Okay, so there is no good model to be found here. If you look at, let me look at a different angle just to make this clear to you. This is a little bit difficult to see. So the problem here is that XOR cannot be classified using this model. So the model converges, but it converges to the wrong value. So just because something converges doesn't mean that it is great. It simply means that it converges, but the original model, that model which is there within our hands, is a bad model. Okay, so that's the important lesson of running XOR through a logistic regression. In the next video, I'll actually show you how to run XOR. I'll just restore this code to the original code so that when I share it with you guys, you have the right code. But in the next video, I will show you how to run XOR through a neural network so you actually get a proper correct prediction. So for example, when you come here and look at the prediction here for the XOR that we had, let me see whether that exists here. YH is what I think I called it. I seem to have called it something else. Let's just check this back. This is important. So I'll restore this and run this once more. We'll continue this. The model here was stored in Y hat, but that model is not sitting here, I suppose. Okay, sorry, it's not sitting here, but we can simply check that the ground truth when you said 0, 0, 0 is obviously not going to be great. Okay, it is simply going to be sigmoid of 0 every time. So you are going to get 0.5, 0.5, 0.5, 0.5. So that's our prediction for all 4 cases here, which you can see here. It's just 0.5 throughout. Okay, so you can see when you look at the left that the actual prediction, which is this green square, is regardless of what value I give for x1 and x2, it's 0.5 at every single case. So that's not a great model, but what we will show is we will get the XOR prediction if we use a neural network with even one hidden layer. So we will see that in the next video. Thank you.